This is the second lecture on analysis of variance for Chapter 13, Stats 253, and in this lecture we'll discuss ways of using R to perform the analysis. In the first lecture, I showed how to perform it by hand. From the first lecture, you might say that this is a very straightforward but tedious calculation, and it would be quite a bit of tedious work and perhaps rather error prone to do it by hand, and that's why we have software to do it for us. We'll also use the software to perform analysis of the means. If we find that one stands out from the other by this analysis that we did by hand that we're going to do here right now, the next question is, which one is it? Or which ones are the means that stand out from the others? And we have some analysis to do that, to answer that question as well. Okay, using R, which is or rather my software of choice for you, we can use a data set, and the one is the weights of different chickens given 4 different kinds of diets. So obviously with 578 different weights, we really don't want to do this by hand. Okay, we will have the same calculations. Some of them are going to be done automatically. We'll have the same degrees of freedom. So for the treatments, it's the number of treatments minus 1. In this case, we'll get a 3. And for the degree of treatments for overall one for the errors is going to be the 578 minus 4, giving us a 574 for the other degrees of freedom. And we can feed this information very easily into R. The R command is AOV. Don't put any N or any extra letters in it. It's just AOV, and all you have to do is tell it the variables, and you want weight as a function of diet. Okay, I always give mine a name, but if you don't give it a name, you just get some information out. But let's look at what I get out from the summary. If I take the summary of that, I said, then I can get out some of these variables without even putting in. It's going to go and count the number of subjects. It's going to count the number of treatments. It does all this automatically. This is very nice. So we had these degrees of freedom, and if you remember from the previous page, one was 3 for the number for treatments, and in terms of the error it was 574. So it just gives those to you right there. Then there is the if you remember, there's a denominator and a numerator to calculate the F, and the denominator had a big sum in it, and then you divided by 3, or rather it was a numerator had a big sum in it and you divide by 3. The denominator had another big sum in it, sum of variances, and you divided by the other degrees of freedom, which was 574. Okay, so here what they give you here are those sums that go in the numerator or denominator before they're divided by degrees of freedom. Then they take the 155,863 and divide by 3, and here it is divided by 3. Now it truly is the numerator for the F value, and the next one they divide by the 574 and truly get the denominator. Okay, they divide the numerator by denominator and you get the F value. This is the F test value. So you see the calculation is sort of laid out here without you having to do anything other than feed it the data. Okay, now what you do with the F test value is compare it to the F critical value. You don't know the F critical value. You can get it, and we'll get that we'll get it in a few minutes, but right now you don't even know what it is. But you could also look at the p-value associated with f. That would be the area under the f distribution curve that is to the right, that is beyond the f-test value. Okay, and here it is. 6 times 10 to the minus 7. Of course, that's quite significant, and so there you go. The f is the null hypothesis would be rejected, and in this case, one of the diets did make a significant difference in the weight of these chickens. Look at this code right here in case you hadn't noticed this before. All right, what do these different asterisks mean? Here's the significant codes right here. Okay. If you have the 3 asterisks, that means that this p-value is less than 0.001, which would correspond to less than, well, 99.9% confidence level. If it's 2, it's 0.01. 1 is 0.05, which is a 95% confidence level. In other words, these are the alphas. It just gives you an idea of the alphas, and they just write it here as a symbol, and that's what these significant codes mean, in case you need that translated for yourself. Okay, so we have determined that the 10.81 is way out in the critical region, and the null hypothesis can be rejected. Now let's look at it the other way. If you want to find out what the F critical value is, you can also do that from in R. You feed it, use QF. Remember, to find the critical value for a normal distribution, we use Q norm. For the t distribution, you use QT. Here we're going to use QF because we're using F distribution. You feed it alpha. Then you have to feed it the 2 degrees of freedom, and you have to do that yourself. And of course, say lower tail equals false. We're interested in the right-hand tail, not the one by the y-axis. So for 5%, for 95% confidence level, alpha would be 0.05. Here, the 2 degrees of freedom, we'd have to feed it themselves. Before, all we had to do is give it the data. Setting the lower tail equals false. We find a F critical value. That's what this is. So here is F critical. And you can see that the 10.81 is much greater than the 2.6, and that just confirms what you already knew from the p-value. So you see, by using R and other software packages as well, performing this analysis is quite easy. You really didn't need to do the F critical value. That was just for information. You had everything you needed from just typing in the command AOV. But now we're going to move on to the next and the final piece of analysis that we're going to do here, and that is to determine which one of these treatments actually is significantly different from the others. Now, if you have a list of these treatments and you have all these means, how can you find the one that's different from the others? Well, one way to do it would be to use t-distribution and compare each 2 means pairwise across your whole experiment. Well, if you have a lot of treatments, this could get out of hand very fast. Also, there's some other chances that you might come up with spurious results. So that is not used. Instead, what's used is, it's right here, a Tukey analysis. Tukey is the name of a statistician, and it's usually followed by the letters HSD for honestly significant difference. Okay, so that's what the HSD stands for. And this is analysis. Once you have performed your analysis of variance and found that at least one of the means is significantly different from the others, then you need to go through and figure out which one or ones are different. Right. Instead of using actually this t-distribution, this analysis uses something with a q in it, and it's slightly different from a t-distribution, but it's very similar to it. And what it's based on is the difference between the largest mean and the smallest mean across your experiment. So you take the largest and subtract the smallest from it. Also, you have an idea of the variance across the experiment, and from that you calculate a coefficient. So instead of T alpha, you have what's called a Q, right? And that's used to determine a confidence interval for the difference between the two pairs. Okay, that's a lot of words. We're going to use the software to do it, so let's see what we get here. Well, here's the command first. This was the variable we got that I used for the analysis of variance for the chickens. Right? So this is the result of the analysis. Okay, let me write that right here for you. If you remember previously, and then okay, here was the command in R for the analysis. I stored the results in this variable. So whatever variable you choose to store the results in is the one you're going to feed into the Tukey analysis. The command for the Tukey analysis is TukeyHSD. Okay, and this is the result of it, and then it's going to be more on the next page. So this is the R command for doing the Tukey analysis. You give it the variable name of the analysis that you performed earlier. And this is what you get out. Alright, let's just look at what we've got here. This is a comparison between the mean for the second treatment group and the mean of the first treatment group. Here's a comparison for the third treatment group to the first one. Here's the fourth to the first one, 3 to 2, 4 to 2, 4 to 3. There you've got all of the pairs of different means compared with each other. The next column gives you that difference. So this difference here would be, and the first column would be the mean from the second treatment group minus the mean from the first treatment group. In that case equals something like 9.97. Okay. Now using that Q value, which is similar to a T alpha value, various a confidence level, as it said on the other page, for 95% confidence. This confidence interval rather is computed, and here is the lower part of the interval, and here is the upper part of the interval. All right, you can see 19.9 is in the middle of this somewhere. All right. Now, if this is statistically significant, you're going to want to associate with some sort of a p-value. Here's a p-value. It's called adjusted because it's adjusted by this Tukey analysis. And supposedly, this Tukey analysis makes it harder for you to get a significant p-value that will lead to a spurious result. So let's look down here at this p-value right here. 3, comparing the third treatment to the first treatment. Here is the confidence interval here. Notice it doesn't even include 0, which we like because there's such a difference between it. And look at the adjusted p-value here. It's very, very small. This has significant difference between 3 and 1. Look at 4. Again, you see a very small p-value. There's a big difference between 4 and 1, between 3 and 1. How about between 3 and 2? That p-value is 0.1. No. Between 4 and 2 and 4 and 3, no, they're just about identical. And this one is questionable because it's a little greater than a 95% confidence. So this is kind of questionable. These two are significantly different from each other. These two are not. These three are not. Combinations are not. So when you do your homework, you'll see very similar results. Remember, the commands are very easy. AOV, and the other command is TukeyHSD, and that's it, and all of it's done for you automatically. And now, final word, you can remember those articles I had you read on hypothesis testing when it talked about how software actually contributes to the problem of doing statistical analysis and not really studying the data. So it's a good idea. Plot out some of those Q plots, study them, look at them, and understand what you're doing. Software does give you very easy results. They look very professional, and therefore they must be correct, but it's up to you to determine if they really are correct and if they really are significant. So this is the final lecture for Stats 253.